Welcome to the continuation of our lesson on plastic analysis of slab using the E-line method. This is actually part 3 of the lesson, so if you have not watched part 1 and 2, kindly watch them so that you'll be able to get what we are doing since this is a continuation. So in this last part, what we are going to do will be to solve the tutorial question 3. In our part 1, we solved tutorial question 1. In part 2, we solved tutorial question 2. So in this part 3, we are going to solve tutorial question 3. So this is tutorial question 3. We have been given a rectangular slab of dimension 8 meter by 5 meter. So let's read the question so that we understand. The question says, for the slab shown in figure Q3, side AB is continuous, BD and AC are simply supported while side BD is unsupported. The slab is carrying a design load of 19.35 kilonewton per meter square. Assuming the reinforcement provided across the shorter span has a moment capacity M, and that provided across the longer span has a moment capacity 0.7 M. A. Select what you consider to be a realistic E-line pattern and calculate the value of M. B. Repeat the process for 2 additional realistic E-line patterns and using a safety factor of 1.1, determine the value of M you will use to design the slab reinforcement. So that is a question. We are told that AB is continuous, while side AC and CD are simply supported and side BD is unsupported. Always take note of this unsupported edge because that will influence the where our E-line or the selection of our E-line pattern. So we go ahead to the solution. The solution to tutorial question 3. So this is a E-line pattern that we have. This is a rectangular slab of 8 meter by 5 meter. The E-line pattern is such that you can see the whole of this plate. Okay, first of all, this is the Hawking E-line inside AB that is continuous. You only have Hawking E-line on the continuous edge. So this is the Hawking E-line. And after that, this is a sacking E-line. This AG and CG and GH are the sacking E-line, while this dotted vertical line are just to divide this into triangles and rectangles. We don't want to start dealing with trapezium. So having done that, you also will notice that the whole of this plate 2 and 3 will rotate about HAB. The whole of plate 3 and 5 will rotate about side CD, while plate 1 will rotate about side AC. There is nothing rotating about BD because BD is unsupported. Always take note of that. So this unsupported edge influence the selection of a E-line pattern. So these are just cutting sections to see, so you might not bother yourself much about this. The next thing we want to establish, remember the question says the reinforcement across the long span, that is a horizontal reinforcement, it has moment capacity 0.7 M, while the reinforcement across the short span, which is the vertical reinforcement, has moment capacity of M, and we have been given our UDLW to be 19.35. So what are we to calculate? We are to calculate the value of M, the moment capacity. So first of all, as usual, we go to calculate our external work. Go ahead and calculate our external work. In this case, we have plate. The plates are different. Plate 2, plate 3, plate 1, plate 4, plate 5. So we go ahead and calculate for each of them. For plate 1, we have our N delta. The N here is the load, and the load we will have it by calculating the plan area of triangle, the triangle in plate 1. and multiplying it by the UDL, which we have been given to be 19.35. So we go ahead and do that. Our half, the triangle here is 5 times 2.5 divided by 2. That is our triangle. This is our delta, the displacement. Because it is a triangle, we use 1 over 3. And this is our W, 19.35. And that gives us our external work for plate 1. So we calculate for plate 2, we calculate for plate 3, we calculate for plate 4 and plate 5, taking note of their shapes. So having done that, we now come to calculate the sum of external work done, that is summation N delta, which is this for plate 1, plate 2, plate 3, plate 4, plate 5, and that gives us 381.62 kilonewton meter. That is sum of energy for all the plate. The next thing we go is to calculate the Hawking moment. The Hawking moment, we have one Hawking heel line, Hawking heel line AB. So this is how we calculate it. This is Hawking heel line AB. Remember, for this Hawking heel line AB, the reinforcement that will resist it is a vertical reinforcement that will be going like this. The vertical reinforcement, and we are told that vertical reinforcement has a value of M. The vertical reinforcement has a value of M that was told, we were told that in the question. So take note of that. So when we go for AB, ML theta, what is our M? Our M is actually also M. What is our L? Our L is the length of the heel line, which is 8 meters. And what is our theta? So if we stand here, this is the point of our maximum displacement. This line GH is a point of our maximum displacement. So that distance is what? 2.6. So our theta is 1 all over 2.6. That is how our Hawking heel line is 3.08. So we go ahead to calculate our sacking heel line. Please take note, this is where you need a little more explanation. Let's start with sacking heel line AG. Sacking heel line AG, remember I will have the vertical component and the horizontal component. So first of all, we calculate the vertical component. The vertical component, remember this vertical component, which reinforcement will resist it? Is it the vertical or the horizontal? It is a horizontal reinforcement. The horizontal reinforcement is what will resist that vertical component. And the horizontal reinforcement, we were told it has a value of 0.7 M. Please, let's take note of that. So when we are calculating the vertical reinforcement, we have our M to be 0.7 M, because the vertical component, the horizontal component, is the one resisting the vertical heel line. So it has a value of 0.7 M. Let's take note of that. The length of the heel line here, the length of the heel line is actually, what is the length of the heel line? The length of the heel line, this place should be 2.6. Let me have a look at it. Okay, for the heel line we are calculating, this vertical heel line, the length is 2.6, while our theta, this is the vertical heel line, the distance from the way it rotates is actually 2.5, so that is why our theta is 1 all over 2.5. Now we go ahead to calculate the horizontal component. The horizontal component will be resisted by vertical reinforcement, and the vertical reinforcement has a moment capacity M. Please, let's take note of that. So for this horizontal heel line, the horizontal will be resisted by vertical reinforcement, which has a moment capacity M. So that is why we come here for this one now. The length of the heel line, horizontal heel line, is 2.5, and the value of moment M is M, while our theta is, if you look at this one, this place of rotation, and the distance from that place is 2.6. That is why our theta is 1 all over 2.6. And when we calculate the whole of this, we have 1.67. And so we go for E line CG. E line CG, second E line CG is similar. We calculate the vertical component and then we calculate the horizontal component. So again, we start with the vertical component. For the vertical component, this is vertical, it will be resisted by horizontal reinforcement and the value is 0.7 m. That's why we have 0.7 m, and the length of the vertical component is 2.4, while our distance from this distance is 2.5, so our theta is 1 over 2.5. We now go ahead to calculate the horizontal component, which is this one. The horizontal component will be resisted by vertical reinforcement, and vertical reinforcement has value m. So we have m here, while the length is 2.5, and this is our, the length is here 2.5, and the distance from this place to point of rotation is 2.4. That is why our theta is 1 over 2.4, and so we do that, we have 1.71. So the next one is E line GH. E line GH, you remember you will calculate the rotation on plate 4 and rotation on plate 5. So that is what we are going ahead to do. So first of all, we calculate for rotation on plate 4. We have here that the length of the heel line is actually 5.5. So we have 1.5 with 5.5. For this heel line, which is horizontal, so it is the vertical reinforcement that will resist it. That is why the moment capacity of vertical reinforcement is m. That is why we have m here. And from this place to here, the distance is 2.6. That is why we have our theta as 1 over 2.6 plus. We now calculate the one due to plate 5. That one, the length of the reinforcement, the length of the heel line is still 5.5. The moment is still m because it's still resisted by vertical reinforcement. But theta, if you look at this distance, is 2.4. So theta is 1 all over 2.4. So when we calculate that, we have 4.41 m. I will go ahead to calculate the sum of internal energy. So this is for hooking heel line AB. This is for sucking heel line AG, sucking heel line CG, sucking heel line GH. So we have sum of our internal energy as this. So we now go ahead and use our usual equation, summation n delta equals to summation ml theta. So that means that 10.89 m equals to 381.62, and we calculate our m to be 35.04 kilonewton meter. So in this example, we are not going ahead to do the other two heel line patterns. So you repeat the same for 2 more heel line patterns. When you repeat them, the value of m that you have, you select the safest one. The safest one is the lowest value of m that you will have from the 3 heel line pattern. When you have the value, you use a factor of safety of 1.1 and multiply by that m to have the design moment. That means the design moment will, which is MED, will be 1.1 multiplied by your selected m, and your m should be the lowest m you have from the 3 heel line. So that is it from our tutorial question. So thank you for being with us to the end of this lesson. So look out for our next lesson. Thank you very much.